Okay. Good morning and welcome to lecture number 37. In the last two lectures, we looked at two algorithms for single source shortest path, which happened to be a specific implementation of the more generic Ford's algorithm. Today, we'll just quickly look at their complexities and their limitations, and then we'll look at another version of shortest path problem, that is all paths shortest path. We'll quickly see an algorithm for it, a fairly efficient algorithm. Okay, so yeah, so we saw that Dijkstra's algorithm requires a complexity of. So can somebody tell me what was the complexity of Dijkstra's algorithm?
N plus m log n.
So it is. So the number of heap operations that is done is proportional to the number of edges. So it's m log n plus n insertions. So this will be n log n, right? So this is basically order of m plus n log n. This is for Dijkstra's. Now what is the complexity of Bellman-Ford? So we were applying relax n-1 iterations. Each iteration there are m edges, so m relax operations, right? This order of mn. Okay. So if you assume m is order of n square, then Dijkstra's will be order of n square log n. Bellman-Ford order of n cube. Okay. So in any case, Dijkstra's performs much better than Bellman-Ford. In fact, up to a linear factor or up to a n by log n factor. Okay. But let's just list the limitations. So Dijkstra's, the main limitation is no negative weights are allowed. Okay. Whereas Bellman-Ford, no negative weight cycles are allowed. Well, the algorithm will detect if there is a negative weight cycle. So that way Bellman-Ford is more general. I mean, it even works with negative edge weights. But of course, negative weight cycle, there's a problem with the notion of shortest weight walks. So you can run through the negative weight cycle infinitely many times, so and decreasing the weight of your walk. So that way, all these algorithms they will have trouble because they basically build walk. Okay, so it just happens to be paths if there is no negative weight cycle. So that is why what we get are paths. Okay. So these are the things that we need to keep in mind. So whenever we have an application when there is no negative edge weight, we can directly apply Dijkstra's. Whereas the more general case, we'll have to go for Bellman-Ford, but we'll have to pay penalty. So whereas Dijkstra's, in the worst case, will run in time order of n square log n, assuming there are n square many edges, or else it is just m times number of m times log n. Whereas Bellman-Ford can take order of n cube time. Okay. So there are improvements to Bellman-Ford. I mean, so like I stated yesterday, so you don't have to relax every edge. Maybe you can just only look at edges that needs to be relaxed, basically those whose weights have been updated recently. But in the worst case, it will have the same time complexity. It won't really have much effect because you can put large degree vertices, a significant number of them. And once you activate, that is, once you update their weights from infinity to some non-infinity value, you can always ensure that some of them are tens. Okay, so that way, in the worst case behavior really does not change. So we'll, for all our purposes, we'll be taking this as the worst case time of Bellman-Ford and dice-Kras. Dice-Kras you can improve a bit. You can take out this log n factor from M if you use amortized analysis for Fibonacci heaps. So if you use Fibonacci heap implementation, this can be improved a bit. Okay. Okay. So today we'll look at another variant of the shortest path problem. So remember that in the first variant that we have studied, we have a fixed source and we want to know all shortest paths originating from that source. Okay. So in all pair shortest path problem, we want for every possible pair the length of a shortest such a shortest path between them from one vertex to the other. Okay. So again, the context is the same. We have a directed graph with edge weights. What we want is for every pair UV, length of a shortest path from U to V, also such a path. Okay. So let's just look at so one straightforward thing is you already have single source shortest paths. We will be using it. So we'll just analyze how to use it and how to improvise their application. I mean usage of single source shortest paths. And then finally we'll give an independent algorithm which is of similar complexity. Okay. So one notational issue is like, okay, so we need a notation to represent shortest paths. So earlier we just said, okay, for every vertex, distance v is what we are going to compute. So instead now what you do is distance will have two parameters. Distance uv represents shortest length of a path from u to v, shortest length, okay, the shortest path. So weight of a shortest path. Okay. And similarly, now the predecessor relationship, we can just have two parameters. Pred uv, basically the previous vertex in the shortest path from u to v. So previous vertex from v. Okay. So this basically solves the issue of representing these paths. So you will be having, so for every u, so predecessor u star will basically represent the shortest path tree for paths originating from u. Okay, so that's yeah, simple modification. Yeah, so that is a minor thing though, but yeah, it's necessary. Okay, so now let's just do this naive implementation. Okay, so we have dice-Kras as well as Bellman-Ford. We'll run all of them. Okay, so each of them on every vertex as a source vertex. So that is one way of approaching all pair shortest paths, right? So let's just see what happens if we do this. So for every vertex, we run dice-Kras with v as a source node. Then the running time will be, so m log n for single run of dice-Kras, it will be multiplied by n. So this will be total of n m log n. So I'm just assuming the regular heap implementation, not the Fibonacci heap implementation. So this will lead to order of n cube log n. Okay. So if you use Fibonacci heap, there will be a slight saving there. Okay. This will be order of n cube. But what are the limitations? Negative edge weights are not allowed. Okay. So this running time also comes with a limitation where negative edge weights are not allowed. Now, whereas if we use Bellman Ford, so same thing, you just run Bellman Ford for every vertex V as a source node. Okay. So the total cost will be, so Bellman Ford takes order of mn time. We'll be running it n times, so this will be order of n square m. In the worst case, this can be order of n to the 4, assuming m has order of n square edges. Okay. So, limitations is a order of n factor versus than vice cross. Okay, but advantage, negative edge weights are allowed. Okay. So yeah, so this is kind of trade-off. I mean, if you want really fast implementation, then dice cross would be good. But then there is a limitation of negative edge weights. Okay. So see, this problem has been studied for maybe 50, 60 years. Okay. So in the 50s itself, people started 50s or 60s, soon after dice cross came, I think. So people started, okay, maybe can we use dice cross even for negative weights? Well, that is crazy, right? Because we know that dice cross won't work if there are negative weights. Our proofs just fail. They don't work. Okay. But here is an idea. Okay. So the question is, the thought is, maybe we can modify the weights so that the graph does not have negative edge weights. Well, so if you say have a graph, some graph. So this is minus 10, 5, minus 7, 3, 6, minus 6, and so on. Okay. Now, what is the obvious way of getting rid of negative weight? You just add large positive value. Say add plus 11, plus 11 to all of them. Some value larger than the absolute value of the least weighted edge, that is negative weighted edge. So this will make the weights positive, but we have seen already, we didn't give an example, but I just stated that this won't work. Okay, so if you add weights so that edge weights become non-negative, then the shortest paths change. Okay, so the graph has completely different shortest path structure. So shortest paths go crazy. So you can't retrieve the shortest paths in the original graph. Okay, so that is a problem with that. So adding negative weight edges, I mean adding weights to all edges uniformly will not work. Okay, but the hope is not lost, so that you can actually come up with a clever way of doing it. Okay, so yeah, adding a fixed weight uniformly does not preserve the shortest paths. Okay, but instead you can imagine the following. Okay, suppose for each vertex V there is a price associated with it. Okay, so the price associated with it, you can just imagine. So you get the price, or you get that money if you are leaving the vertex, and the price you have to pay if you are entering the vertex. That is something, just an imagination. I mean, there is no justification for it. Okay, so what we are going to do is, if you have some price associated with each vertex, so then we can try to set weights, modify the weights as following: the weight of the original edge plus the difference between the prices. So this is the gain that you are going to make if you are leaving the vertex U, This is a loss you are going to make if you are entering B. Okay. Now this kind of modification, I didn't tell what is pi. Okay, so pi, these are some numbers, let's suppose. Okay, of course we need to come up with these numbers such that these are all non-negative in the end. Okay, so that is going to be our challenge. But look at such a modification. What does it do? I mean, why is it useful, such a modification? So what we do is, so let's take an example graph somewhere. An empty page. Okay. Sorry. L here. Okay. So take some graph. Okay. With possibly negative edge weights. That could also be parallel just this way. Okay. Say -5, -3, 2, 6, -7, -1, 10, 5, 16, 3, etc. Okay. 8. Now let's say we have some numbers associated. So this is 7, 3, 30, 12, 6, 5. Okay. Now if I modify, so this is pi b. Okay, so this is pi. So let's say vertex is A here, B here, C, D, E, F. Now, so the weights are modified. So let's suppose we modify the weight the following way. So weight of 5, 7 is equal to -5 plus 5 minus 7. Okay. Weight of, not 5, 7, sorry. What is that? Weight of AB. Okay. So weight of BC is equal to -3 plus 7 minus 3. Okay. Weight of DC is equal to 2 plus 30 minus 3 and so on. Okay. Now the nice thing about this is, so you take any path. Okay. So if you take any path, so the length of the path does not change by much. Okay, it does change, but it does not change by much. So the source node and the destination node, so the difference in their whatever the price values will be the change in the path length. Okay, so what happens is there is a telescoping that happens. So all intermediate contributions of these prices will be cancelling. So if you take this path, so consider the path A, sorry. So rho be the path A, B, C. Okay. Now, so weight of ABC or weight prime of ABC will be weight of, sorry, weight of AB plus pi A minus pi B plus weight of BC plus pi B minus pi C. This is what you're going to get. Okay. Now these get cancelled. So there is a kind of telescoping that happens. So now if you ensure that this is some harmless value, so the source and destination will have a harmless value, then we can ensure that paths are preserved, particularly the shortest paths are preserved. Okay. But the only challenge is what are these values? So these values are not defined at all. Okay. So the point is it's possible to come up with such values. So if you have a fixed source and destination, you can preserve the shortest path. Okay. So maybe what you can do is you can ensure that these two have the same value. So if this difference is 0, then the short length of the path is preserved. Okay, so length of any such path is preserved. Now the question is it possible to come up with such a pi? That is an interesting question that we don't really know. Okay, but what we can see is this kind of modification can be made to be harmless. Okay, so this kind of modification preserves shortest paths. Now the only challenge is how do we get such a modification? So, or in other words, how do we come up with such a price associated with each vertex? Okay, so this is only a thought so far. I mean, the idea is like, okay, if you associate a price and then for every edge weight, you modify the weight of that edge by adding the price difference. Okay, so this kind of helps in preserving shortest paths in the sense that there is a telescoping sum that happens. So with the suitable values for pi, you can actually preserve shortest paths. Okay, but now the suitable choice of pi should be such a way that even if the original graph had negative edge weights, the edge weight of the modified edge weights as per this modification should be non-negative and the shortest path should be preserved. Okay. Yeah, so those are black boxes. Those we haven't addressed. Okay, so this is only a thought process where if you can do this kind of modification with a suitable choice of pi, we can preserve shortest paths. It's basically because of telescoping. Yeah.
Hello, sir. Okay. So, what do you mean by telescoping? I'm not understanding that term.
Yeah, so this is called telescoping sums, right? So this telescopic sums, if you remember, I mean, I don't know, you must have seen. So if you have a summation, right, all intermediate values cancel. This is called telescoping.
Okay, okay.
Yeah, so I mean, if you have, okay, here we have only length 3 paths. If you have a longer path, right, so take this path. Okay. So now, so weight of 5 minus, sorry, pi 5 minus pi 7. This will be pi 7 minus pi 12. Sorry, pi a minus pi b. This will be pi b minus pi whatever. This is e. Then this will be pi e minus pi d. Right. So now pi b and pi d, pi e will be cancelled. Right. So that's called telescoping. So only the difference of pi a and pi d will remain. So that's called telescoping sum.
Sir, can we take pi as the maximum negative edge? I mean, pi of a vertex is equal to the maximum negative edge present in the graph.
Okay.
So
For every vertex, it's the same value.
yes, sir.
And then it won't make any difference, right?
Okay.
It will be like adding a 0.
Okay. Okay.
Yeah.
Hello,
Yes.
sir. Like I'm not able to see it, but how this modification is preserving the shortest path?
So this, yeah, that's, I mean, I just leave it to you to argue it out. Okay, so this basically preserves the shortest path, but like I said, I mean, the value addition, right? So see, for you, if you take any pair, okay, uv, okay, now for any u to v path, length of the path will be modified by the difference between the price values of u and v, right? It will be basically pi u minus pi v. So all u to v paths, they will have the same addition. So the weight of their path will be added by this value. That's it, uniformly. Then the shortest path will remain the same, right? See, now for any a to c path, the new weight or weight of the new path or whatever. So the new weight of the path will be basically weight of the original path plus this difference, pi a minus pi c. So this difference is uniform for every fixed source and destination, right?
Okay, because of this telescoping sum, it is being constant.
Yeah, for a fixed source and destination pair.
Yeah.
So hence the shortest path will be preserved, right? It will remain the same. If you are adding the same value for every a to b path or every u to v path,
Okay.
the shortest path will be the same. It won't change. The minimum value will not change if you add uniformly the same amount for each of the weight of the path.
Okay,
Right?
sir.
But only thing is this added value is different for each pair, but that does not matter. So hence the shortest path will be preserved. Okay, so I'll leave it to the class to argue it out formally. It's not very difficult. See, the problem here was if you are adding a fixed weight uniformly to each edge, the shortest path, right? Not just the shortest path, the weight of the path can vary. It completely depends on the number of edges in it. So now shortest path can become shortest path and so on. Okay, so that way or a non-shortest path can become shortest path, whatever, because it might be using smaller number of edges. Okay, say shortest path uses 10 edges, whereas a non-shortest path uses only 5 edges. Now if you are uniformly adding 10 to everybody, okay, so the one uses 5 edges will be getting a plus of 50, whereas the one uses 10 edges will be getting a plus of 100. So that can alter their relative values, right? So that way it will not preserve shortest paths, whereas this one will preserve shortest paths because it will be uniformly adding the same value for all paths with a fixed source and destination. Okay, yeah, I just leave it you to argue it out. So maybe I'll write it as an exercise.
Sir, I have a question.
Yeah.
So you said that between two vertices,
yeah,
the shortest path is preserved.
Yes.
But then why are we arguing for the choice of pies?
Yeah, because now you have to get rid of negative weights, right?
Oh, okay.
Pi needs to achieve some objective, right? It has to get rid of negative weights. That is the non-trivial part.
Sir, in that previous example, like you have taken an example and you updated the weights, right? So in that, even when you update the weight, it is negative, the W of AB.
Yeah, so here I put arbitrary value. So the challenge is to come up with these values so that edge weights are not negative. Anymore.
Okay.
Yeah. So here I haven't done that. I've just put some numbers. Yeah.
So the idea is to not to modify individual weights of edges, modify the endpoints of the paths, each path.
No. So see, we will be essentially modifying the weights of individual edges, but you modify it such a way that if you take any path, okay, so in fact, for a fixed source and destination, say A and C, for every such path, the weight difference from the original weight as well as this modified weight will be a fixed number. Okay, it will be, so in this case, it will be nothing but pi A minus pi C. That is pi of the source minus pi of the destination. So you take any, say A to C path. One is this, this. Okay, so all of this will be the weight, modified weight will be original weight plus pi A minus pi C, that is 5 minus 3. This will be original weight plus 5 minus 3. This will be original weight plus 5 minus 3. Okay, so everyone will be getting 5 minus 3. So then the least one will be preserved, right? It will remain the same. So if you have some k numbers, let's say W1, X1, etc., some xk. Now if I add uniformly some number, x1 plus a, etc., xk plus a, the minimum element, say if x1 was minimum, then so will be x1 plus a, right? That won't be, the numbers will be just shifted. And that is achieved by this telescoping. Okay, so if you walk along a path, all intermediary values will be cancelled. It's what matters will be the starting point and ending point.
Hello.
Yes.
Sir, in all these algorithms, we are assuming that these graphs are directed. So won't these work on undirected graphs?
Yeah, undirected graphs, it's a bit challenging. So one standard way is the following. Okay, so when you have an undirected graph, you just put edges in both directions. Okay.
Okay.
But what happens there is, like, if you do that, sometimes it might create negative weight cycles. Okay, so when you have undirected graphs, you don't want any negative weight edges at all. Okay. See, the standard way is that. I mean, there is no separate algorithm for undirected graphs. I think there are, but yeah. So the usual ones, the way you use it, you just put both the edges in both directions. But if the moment you have a negative weight edge, right? If you put edges in both directions, you'll get a negative weight cycle.
But sir, if there's a path between A and C that we found is the shortest path, then that will be the shortest even in C2, even from C to A in undirected graphs. So why do we need to duplicate the edges?
No, we have to be careful when we talk about undirected graphs. That's what I'm saying. Okay. So undirected graphs with the negative weights, it's not. You cannot apply these algorithms right away. You cannot do it.
Okay.
See, for an undirected graph, you have to put bidirectional edges, right, to make it directed, and then apply this algorithm. That's a standard way. But that fails immediately because you will create negative weight cycles.
Yes, I got it.
Okay, so that's why we usually avoid talking about undirected graphs when we talk about shortest path problems. Okay, so if the undirected graph has no negative weight, then yeah, so these ideas work immediately. Otherwise, it's not trivial because you'll have to avoid creating those cycles of negative length or negative weight. Okay.
So finally, if you take every pair of vertices, then the path, like the original path between them is preserved, and if it comes to negative, then you have to add and subtract the endpoints, these pi values. So in that way, it's preserved.
Yeah, so what I mean is, see, all paths will be the same because we are not modifying the edges, but the weights, right, they will be shifted by a fixed value, which is basically the difference between the prices of the source and destination. Okay, so that is all. So they are uniformly shifted by, so if you look at this, right, they are uniformly shifted by a fixed number, all of them. Okay.
Okay, so we need to come up with this endpoint weights for all vertices in such a way that it should be satisfied for all paths, right? So
yeah, not just that. I mean, so yeah, that's. I mean, it won't be uniformly for every pair. So for a fixed pair, it will be uniform. We cannot ensure that it's uniform for every pair. But what we should ensure that the new weights are not negative anymore. See, for example, this is not allowed. So -5 + 5 -7. You will still have -7, right? Whereas this becomes positive. This stays positive. So this weight or these prices that I have given, they're not good because it still keeps this word edge negative.
sir, just a doubt like this. Can we form linear equations here to find out pi's? Because constraint solving kind of thing, right? Like
yeah, but if that will lead to a harder problem. See, what we need to do is we should do it within the algorithmic framework, right? We should not lose efficiency. See, for gaining a factor of n or n by log n, this computation should not be too much, right? It should be within whatever we have so far. I mean, so the running time should be within, say, n cube log n, right? So this computation, the solving of linear equations should be done in that. So whatever idea that we come up with, it should be computable efficiently. Okay. So yeah.
so what is the solution, sir? To find
The
out
solution I've just inadvertently showed it there. So the solution is due to Johnson. So what he does is a fairly simple thing. Okay. So what you do is, so you just imagine the following. So let's have some picture somewhere. Okay. So let's imagine following. Let's assume that there is a vertex S such that you have a path from S to every other vertex. Okay, so maybe I'll read right. Suppose S is a vertex such a way that there is a path from S to every vertex, not edge path. Okay, it's enough to have a path. So that condition is required. I mean, if it does not, if there is no such vertex, then there is a problem. Okay. Now what you do is you measure the distance from S to every other vertex, this vertex, and so on. So your price will be distance from S to that vertex. So pi of u will be distance of u from S. Okay. So just come to the text now. Okay. So Johnson's idea is very simple. Okay. So you take some vertex. This can also be achieved by modifying the graph. Let me not discuss that. Okay. So such that every vertex V is reachable from that. Let's fix it as S. Okay. Now what you do is you compute the distance of V from S. So this can be done using Bell-Munford. So you are running Bell-Munford once. Now the interesting thing happens. So now you modify the edge weights as follows. You take WUV plus distance of U minus distance of V. So this is my pi U, this is my pi V. Okay. Now this somehow magically makes all edge weights non-negative. And every other property is preserved. I mean, whatever we require of pi, right, that is preserved. The shortest paths will be preserved. But this magically makes all edge weights non-negative. Can you see it?
It's by the property of relaxation.
Yeah, it's basically the property of shortest paths, right? So what we have is, so distance of V less than or equal to distance of U plus W. Property of shortest paths. So in other words, this number, so WUV plus distance of U minus distance of V will always be non-negative. Okay. So this at one shot, so only restriction is there should be such a vertex. That also people usually do it by adding a fake vertex and then adding an edge wherever. So yeah, so to every other vertex and so on. Okay, so that immediately solves the problem. You can also put edge weight as 1 or whatever. Okay, that's not really a big deal. What I mean is, so if there is no such vertex, what you do is you just take one new vertex and then add an edge this way to everybody. Okay, to every other vertex with some fixed weight. Say weight as 1 or whatever, some number. Okay, so that is not a big assumption as such. But the gain that we make is now the edge weights are all non-negative. Okay, and that's it. So the shortest paths do not change. So then now what you do? So in one application of Bell-Munford, so what did we do? So we just applied Bell-Munford once, and after that we modified the weights such a way that no weight is negative, but the shortest paths are preserved. shortest paths do not change. Now you run dice cross n-1 times on the remaining vertices. Okay, so that is all. So only magical thing that Johnson did was use this distance. That is a very non-trivial part. Okay, so when we see it, it is easy. I mean, it's easy to verify, but to come up with this non-trivial. Okay, so yeah, so this magical simplification or magical idea of using the distance from a fixed source, that simply works. See, otherwise, so one of you had suggested about equations, right? It gets complicated. Then you'll have to come up with a solution. So here you don't do anything. You just run Bellman-Ford once. That's it. See, instead of running Bellman-Ford n times, you run Bellman-Ford only once. And then the remaining n-1 times, you can use dice cross. Yeah? Is the idea clear to everyone? Now, what is the complexity? Yeah, so this is probably incorrect. Okay, so what I wrote here. So what is the complexity? So complexity is 1 Bellman-Ford. What is Bellman-Ford complexity? Order of mn. And n-1 dice cross. So each run of dice cross, if you take as m log n, then this is going to be nm log n. If you use Fibonacci implementation, then this will be mn. Regular heap. Fibonacci heap. Yeah, I keep on mentioning this because I think many textbooks, they don't really use the Fibonacci heap implementation. Okay, maybe because it's amortized analysis and so on, they'll be using the regular heap implementation. So even if they have discussed Fibonacci heap implementation, they take this as the complexity of dice cross, m log n. Okay, so that's the reason why I also keep on mentioning. I think it is because in practical settings, people don't really use Fibonacci heaps, is what I believe. So what is it compared to the original algorithm with using only Bellman-Ford all through? We have saved a factor of n, right? It would have been order of mn cube, mn square, right? So order of n to the 4, whereas we have done it with order of mn. If you use Fibonacci, otherwise mn log n, only a log n factor array. Okay. Yeah, so this is really a clever idea from Johnson's. We'll not really go into the details and so on. I mean, yeah, there isn't much once we have this here. I mean, we know that the weights are non-negative. Only thing that I want you to prove is the shortest paths do not change with any such pi. Okay, so that is something very easy to prove. So yeah, so this is kind of story of APSP using a single source shortest paths. Okay. So there isn't much non-triviality here. You will have to use both algorithms. That's only non-triviality. Bellman-Ford as well as dice cross, not only one of them. Okay. So apart from that, it's a fairly straightforward application of a single source shortest paths. But people also have tried to improve on or come up with an independent algorithm, dynamic programming or recursive and so on. There has been lots of effort on solving all path shortest paths. Okay. Yeah, in the remainder of the lecture, I'm going to discuss yet another algorithm. It's a very well celebrated Floyd-Warshall algorithm. There are also, I think, a couple of more inventors of the same algorithm. Okay, this is by a simple dynamic programming formulation. And complexity wise, it won't gain much from this. It's pretty much similar complexity. So if you're using Fibonacci implementation, Fibonacci heap implementation, it will be the same complexity. In fact, it could be bad if number of edges is strictly smaller than order of n square. If you use regular heap implementation, so then Floyd-Warshall algorithm will have a log n factor improvement. So, but the interesting thing is the dynamic programming formulation. It's completely different formulation. It's also kind of generally used kind of recursive structure for shortest paths, let alone all pair shortest paths. So I'll just state the algorithm. I'll not prove the correctness and so on. Okay, I'll just state the recursive formulation and state the algorithm. Okay. So the formulation is slightly different. Okay, so usually, so if you try to write a recursive formulation, okay, so to the length of a shortest path, so what you would do is you would try to do a kind of divide and conquer, right? So if you, so I want a shortest path from say u to v, I'll try to break it somewhere, say some vertex x, and then compute shortest path from u to x and x to v. Okay, so that's kind of natural thought process, right? I mean, because of this optimal substructures property, so you can always think of doing divide and conquer this way. Now, I mean, what is x that you are going to choose? That is left to the designer. Maybe the middle vertex that is exactly at the half the length, or that is if you are having a path of length L, then maybe you look for L by 2, or maybe L minus 1, 1, any of that. Okay. So in fact, if you look at Erickson's book, I mean, there is a discussion of all such possibilities and their limitations. Okay. So in fact, that is how the literature worked. I mean, people came up with such formulations. Some of them went into exponential time. Some of them were good, but not better than the algorithm that I have previously mentioned, that is Johnson's algorithm. But nevertheless, I mean, they are interesting viewpoints. Okay. So Floyd-Warshall and also Kleene and I think one more researcher, so they came up with a slightly different formulation. Okay, so with a different parameter. So I hope it is clear when I say, I mean, see, I didn't really give the details. So one way is to apply divide and conquer. Natural thing is you just break the path into smaller paths, maybe 2 or maybe 3, whatever. Okay. That somehow, unfortunately, does not give us better algorithm. Sometimes it even gives an exponential time algorithm. Even if you make it polynomial time with some modifications, improvisations, and so on, it does not really go better than Johnson's algorithm, for example, or even Bellman-Ford. So what Floyd and Warshall did, they gave a slightly different formulation. So we'll assume that vertices are numbered from 1 to n. Okay, so that's going to be important. Now, so they used a different additional parameter for shortest paths. Okay, so pi uvr. So I'm just defining it as distance. You can also use it for path. Okay, shortest path itself. So pi uvr is the weight of a shortest path from u to v if exists, that uses only vertices that are numbered 1 to r. Okay, so pi uvr is only looking at paths from u to v. Okay, so the only vertices that you are allowed to use are from 1 to r. Say r is 10, then only up to 1 to 10. So then clearly length of the number of edges in the path will be at most 10. Okay, so that is true. But yeah, it's not very important as such. Now if you take r as n, then that is the shortest path. If you, so when I say r as n, that means you are allowed to use any vertex. What you get is the shortest path. Okay, so there is a specific value of r for which we get, or there is at least one value of r for which we get the shortest path. I mean, n, or it could be that if every shortest path uses only say n by 2 edges, then for r equal to n by 2 as well, we'll have shortest paths. But for n, certainly pi u v n will be the shortest path. Okay. Is the notation clear? So the only thing is we have a restriction. So pi u v r has a restriction that you're looking at shortest path where all intermediate edges or vertices will be from 1 to r. Nothing else. Now this has a very nice recursive structure here. Okay. So yeah. So u to v, I'm looking at only intermediate vertices from 1 to r. Now how do I split it? How do I go further? So either the intermediate vertices only use vertices from 1 to r minus 1, or I use a vertex r, but then I can break it into two paths. So u to r, which uses only vertices from 1 to r minus 1, and then r to v, which uses only vertices from 1 to r minus 1. See, any path from u to v that uses only vertices from 1 to r as intermediate vertices, okay, there can be of two types. One is it either uses only vertices from 1 to r minus 1, that is this blue colored, or it uses r. Okay, so remember that these are paths, so it uses r only once. Okay, so look at the point where r uses. So until here, it should be a path from u to r which uses only intermediate vertices from 1 to r minus 1. Similarly, r to v should also be a path which uses only nodes from 1 to r minus 1. So this basically gives us the recursive formulation. That is pi uvr is minimum of pi uvr minus 1, that is this case, or this case, which is basically pi of u to r with r minus 1 plus pi of r to v with r minus 1. Now what happens if I put r as 0? It is the base case when no intermediate vertex needs to be used or can be used. That's basically the edge from u to v. So pi uv is the weight of the edge from u to v if it exists. Otherwise infinity, of course. See, only thing is this may not be defined at all. There may not be a path from u to v that uses only vertices from 1 to r. In that case, we just treat it as infinity. Yeah, so this is again a magical recursive formulation. It immediately gives us fairly efficient algorithm. Okay, so this immediately gives us the algorithm. I just show the algorithm. So it's basically 3 loops. So what you do is you initialize this distance. So I'm instead of pi, I'm using distance for the algorithm. So distance uv0 as edge weights if they exist. Otherwise, it's infinity. Then what you do is you increment r from 1 to n. So instead of, so I just took this from the book. So they use v. So this should be n here. So now what you do is, so for every pair of vertices u and v, you compute distance uvr, that is pi uvr. Okay, using the previous recursive formulation. That is basically if distance uvr minus 1 is less than distance ur r minus 1 plus rv r minus 1, then set distance uvr is distance uv r minus 1. Else you set this as the distance. Okay, that's basically this formulation. Either this or this. So if this is a smaller value, set this, else set this. And how do you do it? For every vertex uv, but you have to range r from 1 to n. Okay, so r equal to 0 is already defined, initialized here. So this will run for n. This will run for n into n, again n. So the running time will be order of n cube. This is perhaps the simplest of the shortest path algorithms. Okay, so no extra structure, nothing. All you need is array. So only complication here is you'll need a 3-dimensional array, not 2-dimensional array. So you'll need 3 parameters. It's already 58. Okay, so I'll stop here. So we'll also see a 2-dimensional version of it. So there is this what is known as Floyd Warshall. So this is known as clean Warshall or clean Floyd Warshall algorithm. Yeah, I'll quickly go over this formulation in the next lecture. I will not spend more than 15 minutes. And after that, we will be starting with another topic, or the penultimate topic for the course, that is of max flows and matching. So reminder for the tutorial today. So we'll be starting at 2 p.m. The same link should work. Okay, so you use the same link that we use for lectures. So Srinivasa, can you stop the recording?
Yes. Yes.
So yeah.